Hello, good evening, everyone. For those attending online, we welcome you to the event. But somehow we regret to inform you that we are currently having a technical issue. There's a blackout in the event venue. So we will need more time to fix the technical issue, and we will come back shortly. We appreciate your patience, and we're going to see you very soon. Thank you for coming early.
Yes.
Hello, everyone. We're going to start very shortly. So, welcome for those who are attending online. We are very sorry for the technical issue. We already fixed it, so we're going to start very soon. For those attending offline, welcome. Please make sure that you're already checked in and you have the red, what is it, wristband And if not, you can contact Wira here with the Multibangun shirt. Yeah, and we're going to start very soon. Paldi? Yes. All right. Good evening, everyone. On behalf of the Institution of Civil Engineers Jakarta Local Association, I would like to warmly welcome you to tonight's ICE Technical Meeting. My name is Rifa, and I will be your MC for this evening. Thank you for joining us here at Eastern Promise Kemang and also to those attending online. We truly appreciate your presence and enthusiasm. We would also like to acknowledge that this event is proudly supported by PT Multibangun Rekatama Patria. Tonight's presentation is titled, Why is it so difficult to predict settlement of soft soils? Lessons learned from a trial embankment. Before we begin, I would like to briefly explain the Q&A procedures for you who attend online and offline. For participants on site, you may raise your hand during the Q&A session later, and I will assist you with the microphone. For those joining online, please submit your questions through the Zoom chat or through the Q&A feature, and we will read them on your behalf later in the Q&A session. You can submit your questions from now while the presentation is going, and after and later at the Q&A session too. Now, it is my pleasure to introduce our speaker for this evening, Bapak Michael Dobie. Michael Dobie is a chartered engineer and fellow of the Institution of Civil Engineers with more than 45 years of experience in geotechnical engineering, including over 3 decades working across Southeast Asia. Throughout his career, he has worked with consulting engineers and geotechnical specialists, and notably contributed to establishing a soil testing laboratory in Malaysia to support the North-South Expressway project. Since early 2026, he has been serving as a technical advisor at PT Multi Patria Geotechnic, and he has also been actively involved in the ICE Jakarta Local Association for more than 30 years, and currently serves as chairman of the ICE Southeast Asian Subcommittee. With his extensive experience, we are honored to have him share his insights with us this evening. Ladies and gentlemen, please join me in welcoming Michael Dobie. Pak Mike, the floor is yours.
Thank you very much, Rifa. I hope everybody can hear. I just want to wait until everything is being displayed correctly. Oh, right, there we are. I'd have to apologize for the slight delay just now for everybody online. Unfortunately, we had a power cut 2 minutes before the starting time. But anyhow, we managed to solve the problem, or the venue did, and hopefully it doesn't happen again. Okay, thank you, Valdi, for getting everything ready for me. I would like to just get a laser pointer working. Oh, that's the wrong thing to do. Okay. In that case, I won't try and get, oh no, the laser pointer is here. Good. Okay, well, good evening, everybody, both here in our offline venue and for everybody who is online. Thank you very much for joining us for this technical evening this evening. I chose a title here which might be surprising for people, but why is it so difficult to predict settlement of soft soils? And when it comes to a bit of an introduction, the first question would be, well, is it difficult? I think perhaps, especially for the students who are here, it apparently is quite easy. We get some parameters, we calculate a few stresses and loads, we do a calculation and we get a result. But the problem is then, do we often get a chance to check how good our calculations are when it comes to settlement? And I think the answer is not very often. So today I want to go back to some basics, and the presentation is mainly aimed at the construction of embankments over the Holocene marine clays, which are plentiful around the coastlines of Indonesia, Malaysia, Singapore, Thailand, and so on. So these are very common problem soils. And the main target of what I want to discuss today is how sensitive are the settlement calculations to the parameters used and the assumptions made, things which seem to be apparently quite simple. And to help us, we're going to look at a trial embankment, which provides a lot of very valuable information. It was mentioned by Rifa just now that I was lucky enough a few years ago, as you can see there, to spend 2 years setting up and running a soil testing laboratory in Malaysia. And you can see our team of people there. I'm not in that picture, I'm taking the picture. If you think I am. Actually, the tall and distinguished gentleman towards the right-hand side is Professor Peter Roth, who was just one of the world's very finest geotechnical engineers, sadly passed away soon after this photo was taken. Anyhow, that's an aside comment. I'd just like to mention that in my time with CSL, we carried out a lot of in-situ testing using various techniques. We worked very hard on getting good quality samples and carrying out laboratory testing. And I think a lot of my understanding and knowledge today comes from those 2 years when I really had to get involved in a hands-on way. I also got involved in 2 trial embankments in Malaysia, Muar trial embankment, which is the one we'll talk about today, and another one a bit later on, which was the Juru trial embankment. And certainly when you get involved in these things, you do learn a lot quite quickly about various aspects of behavior of fills over soft soils. Now, before I get into that side of it, let's just look at the idealized settlement behavior. So here we have a cross-section through some soil, and the light brown color is our soft soil. And if you can just see it there at the top, there is a water table, which I'm assuming is either at or very close to ground level, which it normally is in these deposits. That means the soils are all saturated. Now, what we could just imagine is we build our embankment at T equals 0. In other words, instantly, which you can't actually do. But if you want to try to understand the behavior, that's important. Now, if you could do that, you'd get some immediate deformation taking place. And that deformation is not consolidation. It's due to the distortion of the clay mass by the weight of the embankment. And you can see from the lines left and right, it will have pushed the soils outwards a bit, and that's why you get some of this immediate settlement taking place. So the volume change, in fact, is almost nothing. It's a rearrangement of the location of the soil. That's what's going on during this stage. Now, the difficulty is we can never actually see this because we can't build an embankment on at T equals 0. It takes normally weeks or months with putting on layers of fill. So we can never actually see or identify the settlement. So we don't really know what it is because you get mixed up with the early part of the consolidation settlement. Then, as we wait, time goes on, and it could be quite a long time, we get what's called the consolidation settlement taking place, which is due to the expulsion of water from the clay mass. And this depends both on the stress and the time. And we make an assumption that this is completed when pore water pressure, or the excess pore water pressure, equals 0, which never really seems to happen, but we'll get some ideas about that shortly. And then into the longer term, we get a continuation of what's called creep or secondary compression or secondary consolidation, depending on which textbooks you read. And that's an ongoing settlement, which is depending on the effective stress, and it's time dependent. But it's not depending on the expulsion of water anymore. And what you might notice there is I have drawn the settlement roughly half the thickness of the fill. And that's actually about right. That's roughly what we see and you'll see it soon in the performance information. I want to go back to the consolidation stage and just make a point that this presentation, the rest of what I'm going to talk about, is concentrating on the calculation of total consolidation settlement. That's what I'm interested in, because it's the major part of the settlement. So it is the important bit. And I just want to look at a little element of soil, which is in blue underneath the middle of the embankment, and just try to understand how the settlement affects that little piece of soil. There will be some pressures applied. And also one thing that's rather important is submergence. You will notice from the diagram that half of the middle of the embankment is now beneath the water level. So that affects its unit weight or its buoyancy. So that does affect the calculation of settlement. I don't know how often people realize that and take it into account. We'll look at the effects of that a bit later on. So here's a little graph, and I'm going to be showing you quite a few little graphs during this presentation, but we have a graph where we have pressure in the horizontal axis and settlement in the vertical one, and it's the behavior of the little blue element. And there are some important pressures to be identified. We have the initial stress, which we call PI, and the final stress, which is PF. And I've just drawn green lines on there to identify those two pressures. And then there is another, just to let you know, how do we get PF, the final stress? Well, we normally calculate that from the increased stress due to the weight of the embankment. Please be aware that these are effective stresses. So that's only becoming P-F when consolidation is complete. And we need to be aware of a submergence of the fill, as I mentioned just now. There's another pressure, a very important one, called the pre-consolidation pressure. It's there appearing in the middle of the graph, this one here. So what exactly is that? Well, it is what's sometimes called a yield pressure. It's when the behavior of the clay changes significantly as the effective stresses go past PC dash. And it's like this. So at pressures below PC dashed, compressibility is low and the soil is over-consolidated. And it's best to use the MV parameter to calculate the settlement. So of course it's given by a slope of a line. That little red line there is showing you the settlement that's taking place as the pressure changes from P-I to P-C. Then, as pressures go past, or as the effective stresses go beyond PC dash, we'll see a very rapid increase in settlement at a much higher rate. And that's normally going to be defined by what we call CC. And in this case, the soil has now become normally consolidated. And the huge proportion of the settlement takes place during this normally consolidated behavior phase. So what you can see there is that the settlement calculations are going to be controlled by 5 main parameters. And let's just have a look at the effects of one, because any errors in any of those parameters can affect your calculation. And that's what I want to look at really in the rest of this presentation. So what about the effect of PC dash? PC dash turns out to be probably the most important parameter, sometimes very difficult to get it right. And just to show you in a simple way, if I have PC dash too low, then my settlement is much higher than what it should be, assuming that the other one was correct. And if it's too high, then my settlement becomes too small. It is very obvious. And I could make those changes with any of those parameters, and you'd see how the settlement would change. I'm not going to do it for all of them, but just to give you an indication of how sensitive the calculation might be to slight errors or differences in those numbers. Now, later on, I'm going to talk in a little bit of detail about consolidation testing, because it's a kind of natural thing that goes through your head. Said, right, settlement calculation, I need consolidation testing. Well, of course you do. And the consolidation testing is going to give you the slopes of the two lines, the two red lines. You'll get the slopes from that. In other words, the compressibilities. And it'll also give you the pre-consolidation pressure. That'll all come from consolidation testing. And based on that, you can calculate the total consolidation settlement. There are other parameters which come from testing to help you assess the rate of settlement with time. Today, I won't look at that. The main topic is already big enough. So I'm going to concentrate today on the data required for calculation of total consolidation settlement. That's the ones we see there. And I made a bit of a table here, just to, if you like. So you've got to, as an engineer, if you're doing calculations, you've got to assess all of those things. So I put down those 5 parameters in this table, and I've just made a little column there of what it's influenced by. So for example, the initial stress will definitely depend on the soil unit weight and the water level very much. And data smoothing, I'll come to that. P-F depends on how you've calculated the stress increase and will be affected by submergence as well. PC- is a tricky one. There are a number of different ways of assessing it. It's a whole big topic by itself. MV is coming from the odometer testing in the overconsolidated range, and CC in the normally consolidated range, also coming from odometer testing, but you can find it from correlations. There are some very famous correlations for getting CC, and I think people use them, and I want to look at that later on. So now let's go to Malaysia, towards the southern part of the peninsula, and look at the famous Muar trial embankment. I was lucky enough to spend some time working on this project all those years ago. And I want to look at the two controls, which are called schemes 3.2 and 6.6, where the 3 and the 6 are the target thickness of the embankments in meters. There is a rather nice aerial view early in construction. I don't know how it was done, because in those days we certainly didn't have drones. I don't know how it was done. In fact, I meant to ask someone how they took that picture. It may have been with a balloon, I'm not sure. But it's I don't think it was from a helicopter or an airplane, so I'm not sure. Anyhow, you can see the layout of the trial embankment there. It was quite big. In fact, the excuse for building it was a lay-by on the highway. And that's what convinced the MHA, Malaysian Highway Authority, to go ahead with this work. But it had a much bigger purpose than that. Based on the information that was produced, which is a vast amount of information that came out of that trial, there was a symposium held in 1989, which I attended, and that was the first symposium. And then a few years ago, we had another symposium in 2022. And I just want to explain to you why we had the two and the difference between them. So there is the layout of, you can perhaps recognize the shape in this diagram, in this plan view from the photograph just now. And there are two things I want to mention. First of all, the 1989 event was looking at the little embankment there, which was built to failure on purpose. And a very good competition was arranged for everybody to calculate and submit their calculations for the settlement, the failure height of the embankment. And it's an enormous range of values, I can tell you. I can't remember what it was from the highest to the lowest, but it was big. Fascinating, absolutely fascinating work. Then we come to 2022, and the aim here then is to look at the two control embankments, 3.2 and 6.6, and a competition was also set up for people to predict the settlement of those two bits of embankment, now that we actually know it after about 33 years. Here are the cross sections of the two trials. The top one is the so-called 3-meter control, and the lower one is the 6-meter control, as you might guess. It's drawn roughly to scale, and all of those little black markers with the P values by them. Those are piezometers. I've only put a few of them in there, but the important ones, because we'll have a brief look at their behavior in a minute. So that's what the cross sections look like. Just to be aware that although we call them the 3 meter and the 6 meter embankments, they were much thicker than that because of settlement. The 3 meter was a target from original ground level when they reached a certain point in time. So for example, the 3 meter control is about 4 meters thick in the middle. Let's have a look at some information from this. So this is scheme 6.6, and I've done this in terms of pressure. I've calculated the effect of the fill as the pressure at the center of the embankment. And you can see the pressure goes up to around about 160 kilopascals, and it goes up in a series of steps because the embankment was not built in one day. It was built in a series of stages when the contractor could deliver fill and do it. And these plots are the pore pressures, the excess pore pressures. What you can see, I think, quite nicely is, by the way, the bluish colored traces are under the center of the embankment and the greenish colored traces are under the edge. Not surprisingly, under the center is a higher excess pore pressure, and you'll see how the shape of the diagrams roughly follows, or follows quite closely, the loading graph, which is what you'd expect, of course. The pore pressure in those soils which are saturated will react to the load being placed on the top. So really incredible information. And here is the 3 meter control. Of course, the pressures are lower because it's a lower height. And this, luckily, the piezometers lasted longer under this one. And you can see the blue ones under the center, they dropped down a little bit. After about 3.5 years, the pore pressure has dropped a tiny amount. Now, people find this difficult to handle. They expect it to go down faster than that. And it's a problem when you look at real trial data. The green ones are at the edge, so not surprisingly, P1 has hardly got any pore pressure at all, but the other two are affected by the load of the embankment. Okay, so this is what settlement looks like. I've now changed the upper graph to show fill thickness. So you can see fill thickness about 4 meters. And this is settlement going down to what, about 1.3 meters or so. So this is what the behavior looked like of settlement. And this was at the center line of the embankment. There were many other places that were measured, but we'll just look at the center line. That was the settlement. You can see down, it's very well defined, and how you get little jumps next to these little jumps in the increase in pressure. Now, at day 602, they installed a new marker called SM5 on the top surface of the embankment and started to measure it. And in this case, the two measurements are almost identical, which is very nice. And from this, we get the challenge that was given to the people to predict settlement. And it's like this. We said, okay, this is now your new starting point. Please predict the settlement on the 30th of June, 2022, which is that many days, quite a lot later, 12,000 and something days later. Incredible target, incredible challenge to take on board. Now, the way it's drawn here, you don't really get the full sort of scale of what this challenge requires. So I've now changed the time axis. The only thing I've changed here is this time axis now goes all the way out to 14,000 days. And that means that the end point is here. So the target is, based on the data at this end, plus all the site investigation data, what do you expect the settlement to be here? That was the challenge. Absolutely fantastic and fascinating task to be given. And this is the other one. This is scheme 6.6, a very, very similar arrangement. So what happened was that the people were given all of that data, plus all of the site investigation data, a huge amount of data, and they were asked to make these predictions. And there were four people put in their estimates, if you like, their calculations. You can see, and it doesn't really matter about them. Let's not worry too much about this, but there are two from Indonesia. And they each had their own way of doing it. Some of them simply used the existing settlement data. Some of them did calculations based on the soil properties. Some of them did both. Very sophisticated stuff. And these were their settlement predictions of SM5 at that particular point in time. You can see already there is a bit of a variation in the numbers. So what I'm going to do now, and this is the exciting bit, is to tell you what was actually measured. Are you ready for it? This one was 1.37, and this one was 2.34. And you will notice immediately that they are quite different. And this is the reason for the title of my talk. Why is it so difficult? Because this was done in incredibly sophisticated ways. Some very clever work was done. And unfortunately, the results were not particularly close. So that's what I want to explore now. I better watch the time a bit because we had a slight delay at the beginning. If I actually put the actual figures on these graphs, that's scheme 3.2. The red bar is what was actually happening at day 12575, and 666 is like that. So you can see, don't forget, they had to measure from that point. The total settlement is more because you got to add on the extra bit. But that's how it was set up. Okay, I'd like to spend a bit of time talking about the geotechnical site investigation for this site. This was a greenfield site. It was just a plantation area with the occasional kerbau on it and so forth. And actually, this is not the same place, but it just looks like it. Nice green site in Malaysia. And they carried out a very extensive site investigation. They spent a lot of money on it because it was a big thing. And each of the sections of the many had many tests and lab tests, in situ tests, all sorts of things. So what I've done here, I've summarized some of the data so you can see it in a simple way. And these are graphs of the various physical and index properties. So the first one is basically the Atterberg limits and the water content. This is the PI, which we use for quite a few of the correlations. So I thought I'd show it by itself. It's just the length of each of those lines. The unit weight, which is really important. And this is a pizza cone plot, which I want to come back to in a minute. Let's just look at a few of these things one by one. Now, when I first looked at this data, I was always concerned that the liquid limits, especially in this upper clay, were rather low compared to the water contents, which I've never seen before in the marine clays. So I got concerned, was this an issue with the method of testing for liquid limits? And we did some research in CSL, two of my colleagues did this, where we looked at the effect of the preparation of the sample for Atterberg limits. Now, when you do an Atterberg limit test, you take out all material greater than 425 microns. You do it by wet sieving, so you end up with a slurry, and you've got to dry it to get back to do your testing. How do you dry it? Well, there are different ways. You can air dry it or you can oven dry it. Of course, oven drying is much faster. Air drying takes ages. But you could also test in the natural state because there wasn't much coarse material in this clay. So we used 3 different approaches. And when we look on the Atterberg limit chart, the different dots are natural, air-dried, and oven-dried. And you'll see that the liquid limit value, if you take any one set of that date, let's just take this one here, it's easy to see, that the liquid limit goes down and down and down as you go from natural to air-dried to oven-dried. And we found that was consistent. If you've listened to Laurie Wesley talking about these things, he will have talked about this in some of his lectures as well. So the method of preparation of Atterberg limit samples is important, especially if you're going to use the liquid limit or the plasticity index in your correlations, which we do. So this was carried out by a couple of my colleagues at CSL. Some really, really interesting work. So how does it affect the data? Well, if I use the normal Casagrande chart, the blue boxes are as reported and the brown ones are adjusted. And how did I adjust them? I just assumed that the liquid limit should be the same as the water content, which I think is reasonable. And that gave me these brown dots. And if I go back to the reason I mention this is that there are a couple of situations where this is important. We'll talk about Bjerum's correction factor in a minute for vein shear strength. That requires the plasticity index. And we'll also talk about a way of determining CC from the liquid limit. And if the liquid limit is wrong, then your CC is wrong as well. So here they are. So what I've done on this PI plot, These little X's or the sort of the cross symbols, those are assuming that the liquid limit is the same as the water content. And you can see that it's quite a lot higher, especially in this upper clay. And this upper clay turns out to be incredibly important to understand its significance. So there we are. That was, in my opinion, rather important. One other thing that's quite important is unit weight. Unit weight calculates the P-I that you need to know. And one thing that all engineers should do when they get a site investigation report is to plot unit weight versus water content. And I've done that here, and you can see that the dots principally fall on the thick brown line, which is for a saturation of 100%, which is exactly what you'd expect. If you have data points somewhere up here, there's something completely strange about it. Shouldn't be possible. And if you have points way down here, it means the sample's dried out. This little plot is something engineers should do when they get a site investigation report. Do it with Excel or something. It's very quick. So that's what I've been saying. So this is the data from the Muar trial embankment. And what I want to do, though, is to show you something about the unit weight. Now, unit weight is important, and normally the way we actually measure unit weight is from the cylindrical specimens for triaxial tests and odometer tests, because you've got a nice geometry, you can calculate dimensions and weight, you get density, easy. But you need good samples. This can go wrong. So it's rather nice that there's another way of doing it. If the clay is saturated, which in this case it would be, then you can just use the natural water content and the specific gravity using this relationship. Let's not worry about it too much. And from that, we can get unit weight. So it's a completely independent calculation. If I do that, we get rather good agreement. So if you look at the unit weight plot, you've got the red crosses, those are the calculated ones, whereas the specimens are the green ones. So good. This is good news. This means that our unit weights are pretty good. Now, why did I show this data from a pizza cone or CPTU plot? Well, I'm the world's biggest fan of doing in situ testing like CPTU, especially. It's a wonderful test. In this particular case, it's very helpful, but what's interesting is that the upper clay and the lower clay are significantly different, and their contribution to the settlement is significantly different too. Yet this plot doesn't really give you any indication of that. So the point here is, yes, CPTU, wonderful, do lots of them, but you always need some high quality sampling and testing to get this kind of data as well. You still need to do it. You can minimize it with some good CPTU tests first of all, but absolutely vital. Now, something else, you will notice that there's a big change in properties. And in fact, I believe that that change in properties was one of the big reasons for some of those not so good calculations. People did not necessarily appreciate the incredible difference between the upper clay and the lower clay. These are all what we call the upper marine clay, but it's been subdivided again. And it was interesting that if you read carefully the report from MHA, they made a point that there appeared to be a situation where this clay was being deposited in the early Holocene, say 10,000 years ago, and then it got to a certain level and the sea went down again, exposing roughly this level as a ground surface. It's, of course, then the sun gets there, it gets dried out. So you get a slight desiccation and stiffening of the lower clay, which is exactly what seems to happen. And this was described in the site investigation report. And I think this was really important. And therefore, once the sea level came up again, then we got the sedimentation of the upper clay, which was therefore a really young clay, much younger than the one down here by a few thousand years. But that's kind of significant with materials like this. A few words about the vein test. The vein test, one of my favorite tests as well. Very simple test, simple mechanical equipment, but incredibly good data. I don't know how much is used here in Indonesia. I think probably not enough in all the soft clays here, but just some pictures of it. I'm not going to spend much time on it today, just to remind you about it though. Very simple equipment. I mean, that's a colleague of mine doing the testing there. No big electronics, nothing like that. It's all mechanical. Very nice test. And it's done by turning the vane, and from the shear of that, we calculate the undrained shear strength. We do it for a peak case and also a remolded case. And we plot data like this. And this is these are 9 vane shear plots from Muar trial embankment side, and you can see they're very consistent. So when you see data like that, it gives you confidence. It's very nice. Now, if you're going to use, and you should use vane shear strength data, there's a big question which people argue about is, should you correct it? Now, another very famous geotechnical person, Biram, developed a correction technique which is based on the plasticity index. That's why you need to know the PI to choose the right factor. And then the idea is you take your strength from this plot and you adjust it by this factor, which you can see for a high PI can be 0.7. It's quite big. And so that reduces the strength. Now, Biram's work was based on testing in Norway. And then you might say, well, is that appropriate to Southeast Asian marine clays? Well, my experience, it is. From the cases I've looked at of embankments that almost fail, you're wise to do it. It is a totally empirical approach. There are more fundamentally correct ways of looking at this, but I think certainly for initial calculations, I'd be happy to go with Biram's factors, even if they're not excellent. Now, the reason why I'm talking about undrained shear strength, you might say, well, why do you do that when we're talking about settlement? It's because it gives us a way to find PC dash, this very difficult parameter, the pre-consolidation pressure. Mesri, another well-known geotechnical person, developed this very simple relationship that said undrained shear strength is 0.22 times the pre-consolidation pressure. This is one of the really useful relationships in soft soil engineering. And it was valid for a wide range of soils. I've checked it for the Malaysian marine clay, and it certainly works okay. So the point about this is we can get PC dashed out of this by measuring undrained shear strength. But if we're going to use the vane test, we need to correct it, in my opinion. And we'll look at that again in a minute when we look at sensitivity of the calculations. I'll check my timing. Oh, sorry, not too bad. Okay. Odometer test. Automatically, if you're going to do calculations for settlement, you'd say, oh, I've got to have some odometer data. And certainly you do need to have it. And here's some lovely equipment out of a catalog from a supplier in the UK called ELE. So nice, clean equipment. It never looks like that in the lab, I can tell you. It gets all dirty and messy, but it looks nice. It's a very simple test, the odometer test, but it needs to be done well. So what you do, you put a specimen inside a ring, it's circular, and you have a drainage stone top and bottom, and you apply a load, and you have this full of water. Okay, so simple test. And what you do, you measure the settlement, of course, and you keep on increasing the load. And you normally do it in stages, as I've written down there, starting, say, for soft clays at 6.25 kilopascals, and you double it each time, double, 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 double. It's called a load increment ratio of 1. And that's the standard way. And if you buy equipment to do odometer testing, you get weights to do it. So you're stuck a little bit with the weights you get automatically. Anyhow, that's odometer testing for you. Another long story, this one, I can't go into it today about how you can do things better, but let's just accept what's going on for the time being. Here's a very beautiful result. This is a typical marine clay result from the odometer test, where you have the void ratio plotted against the logarithmic pressure. And this is, you can see, that's the over-consolidated behavior here. This is the normally consolidated behavior. That's very clear. And then underneath it, I've plotted some derived parameters, things like the CV value, that's to do with the rate of consolidation, MV, I mentioned already, CC already, C alpha to do with the secondary consolidation. And what you will notice is that they change very suddenly. And they change at a point where the slope of the upper line changes. And this is what is identified as the pre-consolidation pressure. In this case, it happens to be 46 kilopascals. So it's really important to see how this works. The behavior and the properties each side of that line are completely different. And the reason I just say, when you look at odometer testing, or when you look at results from odometer tests, please get hold of the full plot. When you get a site investigation report, you'll have a nice tabulated summary, and it'll give you probably CC, PC dash, maybe CV, and you have to accept it, or do you? You don't have to accept it. You can say, I want to see the full results. I want to understand where you get it from and make my own assessments. I would absolutely recommend you do that when you're depending on those numbers to do your calculations. Check them out. I'll just show you something here because sometimes people don't like void ratio. It's so difficult. Why do you use void ratio in these plots? It tells you so much about a soil. I mean, a void ratio of 3 in a clay is very high. And I've now changed this scale to go all the way down to -1. Why have I done that? Because I can now put a little diagram here where the brown bit are the solids and the blue bit is the voids. So these samples are mainly water. So that's why void ratio is such a good property to be aware of. So let's plot a result, shall we? So I've got some data here, P and void ratio. And we're going to interpret this data. All right, so we'll take E naught as 2.9. It may have been slightly higher than that, but it doesn't make much of a difference. And you're going to plot the data, and you're going to find out what is CC and what is PC dash, which are your two most important parameters in your calculation. All right, here we go. There's the plot. You might say, "Whoa, that looks nice." It's what I expect. You get a very, you get a small slope here, and it rapidly increases. Just what I'd expect from a consolidation test. So what do? I do some trigonometry or some drawing on here. So the first thing I do, I determine where is the point of maximum curvature, which is remarkably difficult, but I do it by moving a circle around. And I then plot some lines. I plot a tangent line and a horizontal line and a bisector. And I then extend the final 2 points upwards like that. And that dot there is identified as PC dash. This is a standard construction which all laboratory technicians will do. They'll do it by themselves. It's part of their job. And that's what goes into your report. And then they determine CC from the slope of that part of the graph. So that's now CC and PC dashed. Good. Okay, we've got them. What are they? 3.349 and 137 kilopascals. 3.349 for a marine clay is pretty good. What do you expect? And the PC dash would mean a little bit deep in the profile. Okay. Now, this test goes up to 400 kilopascals, but maybe the laboratory decides to stop it at 200 kilopascals because they know your loads aren't very high. So low height embankment, why do you need to go up to 400 kilopascals? So they stop at 200 and they do the same interpretation. Let's do that. Okay. And it looks like this because they stop here. So they are told to draw a line through the two final points. So CC is now this slope and PC dashed is that blue dot. And they're quite different. 1.674 and 82 kilopascals. And you're relying on these numbers for your calculation. Okay, I'm now going to plot this graph, and may have guessed this already, with a linear pressure scale. And when I do that, sorry guys, it's a straight line. I was a bit naughty with that. It's a straight line. So there is no PC dash. And you're very unwise to use CC because it keeps on changing. So in this particular case, when you won't get a perfectly straight line with any soil, but you'll get them with the stiff clays will be quite close to that. The best thing to do then is to use a linear parameter called AV, which is just the slope of that line, which is a unique thing. It's easy. And then you divide that by 1 plus E naught, and that gives you this MV. MV we then use, I mentioned it earlier on, to be used in the over-consolidated part of the calculation. So we are. I was a bit extreme with that, but I just wanted to show you how sensitive those numbers can be to the way they are interpreted by a technician in a laboratory who's not particularly interested in your calculations. They just want to do a good job, which they do, but they will do it according to the rules. That's why you need to look carefully at odometer tests. Here are 6 tests which were plotted in the Muar trial embankment report of odometer work, and you can see that they look fairly good. And then these dots, right, so these crosses I put on, these are the interpreted pre-consolidation pressures. One thing you will notice, I hope, is that they all they all fall very close to a load stage. 50 kilopascals, 100 kilopascals, 200 kilopascals. The reason for that is because I know technicians very well. I would always talk to them about this. If they find it difficult, they always put it at the previous load stage. That's why so often they're at those numbers. If I then go and change this to a linear scale here, then you'll see some of them are quite good, probably about right. Others are hopeless. So this is a rather important thing to be aware of. It would be my attitude, my opinion, and this is something our good friend Laurie Wesley is very, very strong about, is that you should always plot these in linear pressure scales as well. It's easy these days. I mean, the data's all in a spreadsheet or something. Plot it with a linear. If you can't see PC dashed on a linear pressure scale, it's not there, which is the case in some of those plots. Okay, last couple of things to mention about odometer test, and that is, here's these series of graphs are everything we need for our calculation apart from MV. We've got the three pressures, and we've got PI. This red line is the pre-consolidation pressure assessed from the vane testing using the Messry approach. We've got CC there, E naught there, and therefore CC over 1 plus E naught. So this little blue trace here is what we might use for our calculations on CC over 1 plus E naught. Now, I mentioned a very famous correlation, which I can't read because it's gone under this thing here, but where you can correlate CC to the liquid limit. I think this was published by Skempton. If I simply do that, I get the red crosses. They are way below what was measured in the odometer. But of course, you could use them. People often like to use correlations, saves them time. And if I do that, then you can see the agreement isn't very good. And in fact, your CC over 1 plus E naught plot, which you need, would be this one. We'll look at the effect of that in a second. Brief word about pizza cone. I mentioned it once already. It is an incredibly good piece of equipment. There will be an event in Bali in September, I think, on in-situ testing. I recommend anybody interested to try to get down there. It's organized by Universitas Parahyangan, Professor Paulus and his colleagues. And this will feature a lot. But you need to be aware, though, of the limitations. Today, I won't go into that. I just want to show you something you can measure. So if you know this piece of equipment, you measure a cone resistance and a local friction. That already tells you something about the soil. With a piezo cone, you also have a pressure element here, which measures the instantaneous pore pressure created by the penetration of the cone into the ground. It's a whole big topic by itself. Today, let's not worry about the details. I'll just show you this particular plot. Unfortunately, I couldn't get the original plots, but these are some plots of interpreted values, where essentially you've got the adjusted water pressure by the in situ water pressure and a corrected version of the cone resistance. But those are nice because you can use those to calculate two additional parameters called AQ and BQ. What are they? Well, AQ is essentially a normalized cone resistance, and this value can be correlated to the overconsolidation ratio. And if you've got that, you've got PC dash. And then BQ, likewise, it's a water pressure ratio, and that can also be correlated to the OCR, and it gives you PC dash. So this is different ways of getting PC dash. I found in this case, the AQ was not good. I was worried that this test may have been done through an embankment and kind of upset things a bit. But if I go back to this general plot, I looked at the BQ parameters and I got these green points. So a bit on the low side, but following the right trend. So you might be considering, yeah, this is giving me a fairly good PC dash. I'll use that. Right, the last part of this presentation really is quite quick. Is to look at the sensitivity of calculated settlement to the assumptions you use. Now, I'll explain the first bit quite slowly, but then I'll accelerate through the rest of it. Otherwise, you might drop off to sleep or something, which I'd hate. But Anyhow, so I want to explain how it works. And then the idea here is to look at the sensitivity of the calculation to different adjustments to the parameters or different assumptions you might make. And I'm going to use the 3-meter control. And there's a nice picture of it. There's it's roughly the right shape. It's roughly to scale. And to do this calculation, I just use a spreadsheet. I didn't use any other thing. And I just divided the layer into particular thicknesses. They're all 1 meter apart from the top. And we've got the upper and lower clays, which are quite different in their properties. And I got the water table at 0.5 of a meter below ground level, which is what we were told it was. So, so I use that as my typical case, if you like, the basic case. That's what I've called it. So the basic case uses that arrangement with the water level like that, and it uses the stress profiles on the next slide, and PC dash is based on the corrected the corrected vein strength divided by 0.22 as per Mesri. Okay, so how does it work, the calculation? It's like this. So we've got all the data we need. So in this over-consolidated bit, so between PI and PC dashed, that's the over-consolidated part, we use MV, and that's how we do the calculation. Very simple little calculation. And then that gives us 287 millimeters. So we're now calculating for the real situation. And in the normally consolidated part of this, in other words, from here to here, we use this formula because it's a logarithmic behavior. So that's why we have a log in there. And this is a very basic equation in all soil mechanics books. And having calculated that, that was 1,538. You see, much bigger than the over-consolidated part. You add them together. So this basic, if you like, my best assumptions give a settlement of 1.825 meters. Quite a lot. Now, please remember, this is only for the primary consolidation. To get the total settlement, you need to include that initial distortion plus the secondary or creep settlement, which I'm not going to look at today. But I thought I would just show you how it works out. If I go back to this diagram, and those were the assessments, and there is the actual. If I put the numbers on here, I made an assessment using an empirical method for this instantaneous settlement. It's not going to be very big. And then my 1,825 millimeters is that bit. There's a gap here, but that's taken into account by the secondary consolidation. So I'm happy with this. I'd have to say that my target here is not to get a perfect result. My target here is to look at the sensitivity of that line to different assumptions, the length of that line. So let's look at these things. I'll speed up, otherwise it's going to take too long. I'm going to first of all look at smoothing the parameters. You might say, what does that mean? Well, you can see that I've had to divide everything into 1 meter layers. Now, if you're using something like Plaxis, you'll be really annoyed by that because 1 meter layers all the way down, you wouldn't want to do that. So you'd say, okay, I will take some kind of smoothing of these values and avoid so many layers. So I've just taken 3 layers. I've smoothed the values. I got something like this, and I've used those in my calculations instead. So that's the unit weight and CC over 1 plus E naught. So it's going to work like, and each time I show you one of these things, there are only a few of them, it'll work in the same way. There is my basic arrangement. In other words, the one I think is the best, personally, the one I think is nearest correct. And there is the 2 values again, going up to a total settlement of 1,825 millimeters. Okay, if I smooth CC over 1 plus E naught, slightly less, 1805, not significant. If I smooth the unit weight, slightly more, 1836. Again, not serious. If I smooth both of them, almost back to the beginning, 1815. So this is good news for everybody. It's smoothing the parameters, as long as you're a bit careful with it, doesn't seem to be too serious a thing to do. Good news, that's helpful. There's one other thing to look at. I want to look at the effect of using that correlated value of CC based on the liquid limit. And it's the corrected liquid limit. And I can't see the numbers here, so look at the screen. 1,099, it's a huge difference. So beware of correlations. Okay, that was that group. Let's have a quick look at this one. What about the depth to the water level? The assumption is 0.5, but maybe it could be slightly different. So let's look at 0 and 1 meter. Same idea. We start off with the basic result like this, and then we look at 0 meters, and you can see the settlement is quite a lot less. And then we look at 1 meter depth, and it's quite a lot more. And I thought, let's look at the effect of this submergence. So if I take my basic arrangement, but I don't include the effect of submergence, what do I get? Over 2 meters. So submergence is important, it's 10%. So please have a look at that and think about it when you do these sorts of calculations. Then the next one is to look at the pre-consolidation pressure assessment, of which there were several ways, but I'm just going to look at the shear strength approach, the odometer test, and the CPTU. And again, I'll be fairly quick with this. I don't want to take too long over this. So here we go. Same approach. Here is our basic result, 1825. We're used to that now. And now let's look at the effect of different ways of assessing the pre-consolidation pressure. So this is using Beerham's factor based on the reported PI values. Remember when I said I was worried that the liquid limit was too low? If you'd used the reported values, you would have got 1632. It's a significant difference. One small thing. If I say, I don't believe in correcting, but I just want to use vane shear strength as it is, I'm not going to correct it, you get 1402, which is definitely much too low. And if I use PC dash from the odometer, which wasn't very wonderful data, I just ended up with a straight line here, 1666. And finally, if I use that BQ plot, which was rather low, with the little green dots on the diagram, not surprisingly, I get a much higher settlement, well over 2 meters. So, almost finished now. Just to summarize all those results. So what I've done here, I've made a little histogram of the different assumptions I was using, where my basic one is here. And hopefully from my little shorthand, you can work out what each of these ones are. What's interesting from this is that if we go from one end to the other, there is a 1 meter range between the extremes, potential for a 1 meter error. And I've only checked one problem parameter in each case. If I combine problems, I think this could have been a far bigger range. Or you may have been lucky and get 2 wrongs make a right, but that's not the best way to do soil mechanics. If I say, okay, well, I think those extreme values are too extreme, I'd never do that. Let's just leave them out. You still get a 0.6 meter variation from the top to the bottom. Significant. So, just about at the end now. I've added some comments on these 5 parameters. Just look at them quickly. The P-dashed initial, generally quite accurate. You're likely to be pretty close because unit weight is not too difficult. You may like to look at sensitivity to the water level, but that wasn't a huge effect. P-final, you're going to do that either by some kind of elastic analysis, or FEA will do it for you, of course, if you're using that. Submergence is significant. The PC dashed, this is the one that can cause the most trouble. And I think the best thing to do is to try to look at it in a number of different ways. If you've got undrained shear strength testing, you can use that, or vane testing. If you've got odometer testing, you can use that. Put it all together, plot it on one graph, and make an assessment of what you think is the right thing to do. I believe you need to correct the vane test data. Oops, sorry. I didn't mean to. MV overconsolidation, that has minor significance. I haven't talked about it at all. CC is important. Be careful with your odometer interpretation. And be very careful with correlations. There are many correlations to get CC from index properties. Look at them in a very cautious way. Please check them against real data. So, last few remarks. Good planning and execution supervision can result in excellent site investigation in soft soil sites. Without a doubt, if you're careful about it, you can do a really good job. I'd recommend always that you maximize the use of in situ testing, especially CPTU and vein borer, which I think are two incredibly good pieces of equipment. But you still do need some high quality sampling and laboratory testing. If you're clever with your CPTU and vein borer, you can minimize the amount of sampling and lab testing, so you can speed up your site investigation. But I would be recommending that highly. Please pay attention to details. Supervise. Doing a test correctly costs no more than doing it badly. Make sure that your things are being done in the way they should. Make sure your samples are not drying out. All these little things. If you have dried out samples, you'll get the wrong answer. So all these little things don't cost anything extra. They just require care and attention. Undrained shear strength is very important because of the way we can get PC dash from it. And therefore, the pre-consolidation pressure is very important. As I said before, look critically at odometer test results. Make sure you're happy with the interpretation. Of course, some laboratories do a wonderful job and their technicians will be spot on and you'll get excellent values, but it is worth checking it because it's such an important test. And try to use more than one approach to determine the main parameters. I think that's a good idea. Now, I got a chance to, because we had a power cut, I think I have an afterword, which will take me 2 minutes. Because I'm sure someone's going to ask me, and you should ask me, what about scheme 6.6? You've shown everything from 3.2. So to save you answering that question, last night I did it. I looked at the effect of this calculation, not all the cases, just the one. So here is my graph, again, just to remind you what we're looking at. The initial pressure is this black line. The red trace is my best assessment of the pre-consolidation pressure. This one coming from, in this case, corrected vein tests. And the final pressure is here. That's scheme 3.2. And my calculation, if you remember, gave me 18.25. For me to now calculate the same thing for 6.6, all I have to do is to increase delta P. It actually was remarkable. I surprised myself last night. It was remarkably quick and simple with the spreadsheet. It looks like that. And I can't read the number. I have to read it over here. 3160. Is that good? Not bad. The total settlement was 3.76. And remembering that this is only the primary consolidation pressure, you'd expect it to be less than that. So I have attempted to plot it on this diagram for scheme 6.6. And I think it's quite good, maybe a bit on the high side. The secondary could be quite significant. But I was happy with that. And therefore, I showed you the slide. No, I think it was quite nice to see how well the approach worked for the different situation. Thank you for your attention. I try to get this into 1 hour.
Thank you, Pak Mike, for your excellent presentation. I think we are now in the Q&A session. Is there any question from anyone here? Any question? Sure. Online? Okay. All right. Is there any question before we give? Okay, I think we have some questions online. Can you see it, Pak Mike? They're from.
Personally,
Yeah.
can you please tell me more about the geomorphology of the Malaysian marine clay at the embankment trial? Oh, Bill Addington is there. Gosh, there's a name from the past. Right, okay. Bill, I'll deal with yours in a minute, if I can. Okay, Mr. Calming type. Okay, the geomorphology of the upper marine clay. I don't know, geomorphology. I mean, this was a deposit that started its life about 12,000 to 10,000 years ago as the sea came up from the last ice age. The sea was about 120 meters lower than it is today during the height of the ice age. And therefore, that was all land surface. The sea came up to roughly the current level. And don't forget, to get a marine clay, this might sound obvious, but the sea level has to be above where the clay is being deposited. Otherwise, how do you get the clay? So they were being deposited in very shallow water because the maximum sea level compared to today. It's been about 4 meters higher during what's called the Holocene high stand. And that was probably the time when the upper marine clay was being deposited. Of course, today there's no deposition of the upper marine clay on land. So I think that's the best I can tell you. I have a lot more information about that question, but I hope that helps a little bit. That's not really geomorphology. It's flat. I mean, it's just a completely level top to the deposit, but I think it's a very interesting one. Right, Bill. Specific gravity value. Yeah, that's a good point. I mean, specific gravity has quite a big effect. It is something that should be measured quite frequently, but what you'll tend to find in one deposit, it tends to be fairly consistent. The time when you get into trouble is when you get organic content. Organic content definitely messes up your measurements of specific gravity, but it is a property which I think should be measured quite regularly and frequently. It's a slightly difficult test to do well, but good laboratories have no problem with that. Right, we have from Mohammed Yushairi. Is there any negative pore pressure observed during conducting CP2? No, not in the marine clay. You probably get it in the sands and the stiff soils underneath, but in the marine clay itself, it's always going to be positive. That's for sure. It's a very young, almost, it's a lightly over-consolidated clay, lightly over-consolidated. Then
From Tariq
Anwar. Can we do tests on Shelby tube samples to get vein shear test? Oh, I wouldn't use Shelby tubes at all. I mean, Shelby tubes are okay for fairly disturbed samples. If you want to sample marine clay, you've certainly at least got to use piston sampling, preferably 75 millimeters. Piston sampling has this incredible benefit that it prevents you compressing the sample as the tube goes into the soil because you hold the piston at the top. So no, I wouldn't use Shelby. If you want to get good data from samples, don't use Shelby tubes. This is okay for identification, Atterberg limits, that kind of thing, water content, perfectly okay. But if you want to do tests, for example, for shear strength, no, it's probably too small for that, isn't it? But anyhow, no, be careful with Shelby tube samples. Oh, Phil's asked a really difficult question. Hang on. Oh, sorry. Was there any effect of seismic load for settlement over this time? Now, that part of Malaysia isn't really very seismic. So normally we would disregard seismic loading in that part of the peninsula. So the answer is no. Any comment on permeability? This is affects, yeah, I purposely said I was not going to talk about that, but Phil's asked me the question now. Yeah, we get good data from odometer tests, but the concern with odometer tests is you're testing a very tiny sample, and it may not include the full fabric. We've also got dissipation tests from the piezo cone. The nice thing about that is it's testing quite a large volume of soil, and that can give you essentially permeability type parameters to help you with your rate of settlement calculations. Generally, if you do that, you'll find the piezo cone is giving you quite a lot higher permeability than the odometer test. But when you're looking at that, Phil, look carefully both on the over-consolidated part of the test and the normally consolidated part, because the CV values will change hugely. And of course, you're interested in the normally consolidated part. So you need to be sure you're down at that end of the information. What kind of ratio between CPT and sampling borehole would you recommend? Oh, this is a good question. I have a whole presentation about this. Can't do it tonight. I can't give you one number. I mean, it depends on what you're finding. But our approach on the North-South Expressway was to use a lot of piezo cone. What we would do, so we have a soft soil site for a piece of highway, maybe it's 2 kilometers long, typical section. So we would do regular piezo cones, maybe every 100 meters to begin with. And then if we found areas with big changes from one to the other, we do some intermediate ones. And then that would give us a really nice profile of the layers. Once we've done that, we would then do vein tests, actually purposely planned against various of those CPTs, not all of them, it would be too many. We would also then plan some high quality piston sampling, which would normally be continuous. In other words, you do one piston sample, take it out, get down to that level, do another one. We would do as much as we could in the way of piston sampling at a small number of boreholes, maybe 4 or 5 in that 2 kilometers. And then we would really do plenty of testing, because then we could relate the laboratory testing very nicely to the kind of behavior you saw from the pizza cone. I mean, for anyone who's done pizza cone testing, you soon start to recognize the traces. You say, oh, that's that soil type. You can see it. It behaves in a certain way. And you can then associate your laboratory work and your laboratory testing with the pizza cone plots. Of course, it requires you do your pizza cone testing very well. That's another lecture, but not today. But that's a really good question. And I think it's something people should be aware of. One thing, please do not do, and it's common. It's like this. I'm going to do boreholes here, and I'm going to fill in with CPT. Disaster. Don't do that. It's a waste of money. You never get a good relationship between the CPT and the borehole because they're some way apart. So don't do the fill-in approach, because many people do, and I may have already given a red face somewhere. I don't know. I think Trevor's smiling at me slightly over there. Okay, so no, please maximize in situ testing, especially CPTU. For some strange reason, it's expensive in Indonesia. I believe it shouldn't be. I mean, you can do 4 tests in a day on a typical site. It should not be too expensive. Maybe you have a better word with the contractors about that. Oh, sorry. Yeah. Oh, Willem. Yeah, Willem. Can you share the link to download the research you just? Yeah, there will be all my information will be provided in a handout by tomorrow. Okay, I'm in charge. Yeah.
But Mike, we're going to give time for Bob here to ask a question.
Okay. Sorry. Right.
Thank you, Mike, and an excellent presentation. My name is Bob Schooler. I cannot overemphasize the need for the testing and achieving the results that you've indicated here today. And I'd like to speak from experience in a couple of cases where we didn't do enough testing that you talked about and the consequences as a result of it. When we were building a conveyor belt in KPC, we had some very soft soil, and we didn't worry too much about it. We drove some short timber piles. They were unsuccessful, and we ended up having to redesign the footings for the conveyor so that we could adjust for the settlement, and they've been adjusting for that settlement for the last 20 years. So we didn't do enough testing in the first instance to understand what the conditions were, and they were exactly as you described. The second example was when we were building the main road between Palanki Raya and Balikpapan. And we came through very soft soils, which is exactly as you've defined here. And the contractor that was building the road couldn't keep the top on the surface. It was settling faster than he could fill to the area. And at the end of the day, in that particular area, they had to end up building a pontoon, a continuous bridge, effectively, because there was no way they could resolve the problems that were not there or that were not aware of when they started the construction. And the third example, which a lot of you will remember, was when they were upgrading the toll road out to the airport here, the last from kilometre 29 to kilometre 34, where it goes around a long left-hand bend. Very soft soils, they were widening the road, and they didn't have the ability to handle continual fill. So it's an area where they tested the soil, they found out what the problems were, and they designed accordingly for those particular problems. So all I can say is to people who are listening and people who are involved in this sort of work, I cannot overestimate the requirement or the importance of doing the testing, getting answers, getting predictions of what the settlement is going to be, not short term, but long term. The Galtim Prima coal conveyor, 30 years of settlement, it's now settled over 2.5 meters. And we've had to adjust the footings for that conveyor continuously every 1.5 to 2 years to keep the conveyor in a straight line. But the settlement has been up to 3.2 meters in some locations. So once again, the importance of doing the testing that Mike has described here, The vein test, I think, is a very, very important tool. One of the I also enjoy getting good results, or certainly good indications of what you're up against. But thanks again, Mike. A very, very good presentation and a very important subject. Thank you.
Well, Bob, thank you for your incredibly good comments to back up some of those points. I mean, that's much appreciated. Luckily, I haven't got to answer your question. It's very nice, but I think it just does illustrate why you've got to get this right. If you don't pay for investigation at the beginning, you'll pay more for it when it goes wrong, I can tell you. So, yeah.
All right. Probably, is there any questions from the audience here? If not, we're going to continue to answer probably like 3 more questions, but Mike, from the online audience. There's a question from Kuku.
Okay, so Mr. Kuku, this is all about not exactly a related topic, but we face challenges during the rainy season when we must complete geotechnical works, including soil compaction and fine soil settlement. Are there any new technologies or methods that could help accelerate soil compaction and soil settlement in the field during rainy season? Well, I mean, without a doubt, people are trying to find better ways for compaction. There are now techniques called intelligent compaction, which are intended to give you a far better result more quickly from heavy compactors. They're not really a field I'm very familiar with. Of course, I think we all have to get involved in understanding what compaction is all about when we build highway embankments and similar things. But I think on the whole, what you know, traditional things you do are what you should still be doing. One thing I would say though is that if you're building a clay embankment, which we often are, is if you're going to control that clay fill, would be to do it through undrained shear strength and voids ratio. It's something again that Laurie Wesley is very strong on, and it's a technique used in New Zealand a lot, where he comes from, and it's a far better way than trying to do lots of compaction tests and then do maximum dry density and water content. So I would recommend a different method of control for clay fills. Yeah, so Carl Mingtai, you're asking again about this business of the liquid limits being below the moisture contents. I think that was wrong. I think that was poor testing technique, and I think I mean, I've seen thousands and thousands of Atterberg limit tests in the upper marine clay, and when they're done properly, the liquid limit and the water content are approximately the same, which is what you'd expect. The place where you see the water content much higher than the liquid limit is in places like Norway, where they have leached clays, the famous quick clays, and that does create all sorts of difficulties. And if you want to know more about quick clays, that's yet another talk. But yeah, so I think that was poor testing procedure myself. I couldn't confirm it, and maybe I'd upset people if I go on about it for too long. But I found that hard to believe, because these were not sensitive clays. Not like a Norwegian quick clay. They're slightly sensitive. What's the sensitivity? It was about 3 or 4, if you remember the vein test profile. Partially saturated soil behavior. Well, of course, these soils should all be saturated. If they're below the water table, they're going to be saturated. So that's one place where you can rely on the slightly simpler approach to dealing with soil mechanics in saturated soils. Really, you shouldn't have to be worrying too much. Only in the fills. In the fills, of course, you need to worry about the partially saturated behavior. Willem's asking about doing numerical analysis. Well, Willem, I'll let you do that because I just use a spreadsheet and divided the thing into 1 meter layers and calculated my stresses like that. And I think the fact that came out pretty well seems to me to be a good confirmation of that. Any more? Theodore, how does this webinar relate to collapse settlement? I think it's a different thing altogether, personally, because we're not looking at collapsible materials. We're looking at saturated soft clays. They're not going to collapse, but they're going to, of course, consolidate, and they're going to change their volume a great deal because they are mainly water, but they're not going to collapse.
I think that's all for the questions from the online attendees. If there's no other questions, is there any?
Yeah, Trevor normally asks a question. Disappointed if he
Hello,
didn't.
Mike. Yeah. How did this all relate to the actual highway? Did they use any of this data for the design? And did the highway settle similarly? And are there any bumps at the bridges where they arrive at the piled bridges?
Right, if you listen in on a webinar on Tuesday, I'm going to cover that. That's a very good question.
You did do
Yeah,
one on
the famous
Tuesday.
ski jumps. Yeah, no. Oh no, they did use these techniques. I mean, in the North-South Expressway, of the entire 800 kilometers, 300 was across marine clay. So this is why they spent so much money on that trial. They wanted to find good solutions. Some of the solutions were a bit far-fetched. There were some strange ones, but they used a lot of vertical drains and preloading. That worked pretty well to reduce the ongoing later settlements. That was quite common. There were certain people who favored piled embankments, but they just caused trouble. But yeah, I mean, the information was used without a doubt. I mean, this was a part of the site investigation. Yeah, and it was fantastic to be involved in such huge site investigation. Incredible.
Okay, thank you.
Okay, Pak Mike. One last question before we close the session.
Oh, from you, Rifa.
No, not from me, Pak Mike. There's an online from David Me. Can
David Mee.
Mhm.
Where is he? Should be here. No, he's in Semarang. Okay, David. Yes, of course. Of course it can. Yeah. In fact, many of the trials in this trial, quite a few of those sections we saw did have vertical drains. And if you look at the full report, which is huge, you'll see that those sections definitely consolidated more quickly. In fact, the fastest one to consolidate was the one with vacuum. It used a vacuum dewatering combined with vertical drains, and that one settled a huge amount very quickly. So yes, these techniques do speed things up, without a doubt.
All right, Pak Mike, I think that's all for the Q&A session. Thank you once again for your excellent presentations and all the answers. We really appreciate your support. And ladies and gentlemen, please give a round of applause for Michael Dobie. All right, on behalf of the Institution of Civil Engineers Jakarta Local Association, I would like to express our appreciation to our speaker and to all of you for attending tonight's session. And we would like to also extend our gratitude to PT Multibangun Rekatama Patria for supporting this event. We hope you found this session insightful and beneficial, and we look forward to seeing you again at our future IC events. Have a wonderful evening, and thank you, everyone. Yeah, thank you. Is the curry ready? I don't think so. I think they're prepared. Thank you, Pak. Okay. Everyone, we're going to have curry, yeah? So please wait for the curry, and we're going to have dinner together. Is it okay to show the announcement or not?